Good morning everyone. Today we are going to have a Smith chart demonstration as well as a DNA demonstration for getting used to the calibration process of the Smith chart. We have already learned that in the theory class how exactly a Smith chart calibration is done. Today we will just touch upon those details in brief and then we will go to the actual demonstration. Now here we can see, here you have the impedance plane. As we know, Smith chart calibration process is basically about transforming your impedance plane into the reflection coefficient plane for a certain frequency range. Because in microwave analysis, let it be a microwave circuits or microwave antennas, everything is wavelength specific. We never specify the absolute dimensions of the device or the antenna. The operations, the response, the parameters are always wavelength specific. Hence, we need to do the calibration process, that is drawing the Smith chart, calculating the reflection coefficient for a certain range of frequencies. Because whatever short open circuit load condition we should define at 7 GHz may not be completely applicable when you go to 1 GHz operating band or 10 GHz operating band. So calibration process is always frequency specific, and in that we are transforming our entire impedance domain into a reflection coefficient domain. This we have seen it in the class also. Okay, so I'll just in nutshell I will tell you what we are doing. We are transforming it all these constant resistance lines as well as constant impedance admittance lines, okay, onto the Smith chart. This is your impedance Smith chart. Okay, we have already seen what is the admittance Smith chart in the class as well as in the practical session. So here we have an impedance Smith chart. So all the constant resistor lines, they are transformed into these R curves or resistance circle, what they are referred to as a constant resistor circle. Similarly, these constant admittance lines, where the imaginary part is there, positive on the top side, negative on the bottom side, are getting transformed into the imaginary arcs. As we have seen, the impedance or the centers of these all arcs lie outside the Smith chart. If you really go get into the reality of the Smith chart, I will just draw. This is your entire Smith chart or reflection coefficient domain, and what we are plotting is only the reflection coefficient values which are less than or equal to 1. There exists a Smith chart for which a reflection coefficient is more than 1, and that is called as the negative resistance Smith chart. We are not going to do that in this current course here with respect to the radio frequency circuit design, but actually speaking, all these regions actually corresponds to a negative resistance Smith chart where mod gamma is more than 1. So here the center, as I said earlier, the center of these are all the arcs, they lie outside. So this is your constant resistor circle and constant impedance admittance circle. Now through the calibration process, which we will explain you using the VNA also, we are basically doing, we are basically identifying 3 points. First is the short circuit point, which gets transformed into this curve, okay, for different values of x. Then we are transforming this 50 ohm or Z0 point, where it gets transformed into the circle which is written over here, and then of course towards the infinite impedance domain, which is basically a point. So these 3 points are drawn, these 3 points are used to calibrate the Smith chart, and then accordingly a Smith chart circles are drawn. So this is in nutshell what exactly the calibration takes place, and remember all these points have to be defined with respect to the frequency of operation, because as we know these values are basically omega into L or 1 by omega C. So evidently it is very clear that all the Smith chart lines have to be mapped with respect to a given frequency spectrum, and hence the calibration process is a wavelength specific or frequency specific. Now before going to the actual demonstration of vector network analyzer, I'll just introduce you to a term called as a network analyzer. Basically it is an impedance measurement device. Okay, there are 2 types which are there. One is a scalar network analyzer and other one is a vector network analyzer. In the scalar network analyzer, we are basically going to measure the scalar quantities, okay, the absolute value of the impedance. We are not at all worried, or we are not at all going to measure what is the phase. In case of vector network analyzer, of which the demonstration we are going to see, we are going to measure the reflection coefficient. And as we know, reflection coefficient consists of amplitude as well as phase. Okay, whereas in scalar VSWR, only the amplitude is present, phase component is missing. So vector network analyzers are the one which we are going to use for the measurement of R plus JX kind of impedance, which generally appears or is present in all types of antennas as well as your microwave circuits. So now we will go to the actual demonstration of the calibration process of the Smith chart. There we will show the measurement process for two different frequency range, because as I said earlier, it is a frequency specific, and two types of antenna measurements we will show using the vector network analyzer. So now we will process towards the vector network analyzer demonstration.